Okay, so hello everyone. Welcome to one more meetup of Deep Learning Sessions Lisboa. Today we're going to have with us David Belo. First, I would just like to introduce us a bit. Deep Learning Sessions Lisboa is a community of people which are interested in deep learning and other topics and are around the area of Lisbon, but not specifically. So if you are interested in this area, deep learning, machine learning, please make sure to subscribe our social media like Twitter and LinkedIn to be updated to future events. Regarding our speaker today, David Belo is currently machine learning team lead at Loca Inc., which is an American software consulting company that works in the area of deep learning. He graduated in biomedical engineering by the Universidade do Minho, and he got a PhD with a focus on deep learning applied to biosignals at Universidade Nova de Lisboa, where he also spent some time as a researcher in the lab LibFiz. Also, he spent some time afterwards working at NASA as a researcher, also with a focus in learning from biosignals. So today, the presentation of David will be mostly focused on how can we learn and how can we create intelligent systems that learn from biosignals. So just to make clear the type of session that we have, normally we have 45 to 1 hour minutes, 1 hour of talk by our guest speaker, David, and then we'll have a couple of minutes later, like 10 to 15 minutes of Q&A, where David can answer the questions that everybody can pose on the chat on the YouTube chat. But if you have any questions regarding the meetup and regarding our like the way we operate, you can ask them in the chat, and one of our team will answer you at the moment. So without further ado, let me just pass to David so then he can make his presentation.
Okay, thank you, Andre. Thank to all the Deep Learning Sessions Lisbon community. This is a presentation a little bit based on my PhD. So it will be most focused on how to use biosignals and how to process them in order to fed them into deep learning architectures. And also these architectures, what architectures can you use, and also some work and some applications that I did during my PhD. And also I will give a brief presentation of my work at FDL NASA. So what is the motivation behind using biosignals, and in why is this so important in today's life? Okay, so healthcare is a driving force. Well, one of the most powerful factors for empowering well-being. So someone cannot function properly if it's not well with its healthcare in good conditions. So normally technology, developed countries have seen a rise in life expectancy, mainly based by the state-of-the-art diagnostics, therapeutics, and innovative technologies. This is always developing it. So these fields should encompass also this moving forward of the healthcare industry. Medical health records, increasing the medical practitioners' accessibility to patient data. So we have storage of databases that include information of patients throughout time and how they evolve. And also there is a quite investment increase with quite nice numbers. So also the accessibility to wearables. So normally now we use human physiological activity in our Apple Watch, for example. There are several wearable devices where you can buy on Amazon and start using them in order. You can collect biosignals using your mobile phone. So, for example, the actigraphy, that is like the acceleration of how you move and how you move, for example. So they are non-invasive, but they are very but they exist and you use them everyday life without knowing it, and also you can have some new technology to use them everyday life and have this data with you. This produces an enormous amount of information. Some of it won't be used, but why cannot be used? Because it's so massive that it's really hard for us for us or for the medical doctor to analyze this kind of information. It's a lot of it. It's too much. So here comes the deep neural networks as one possible solution, as is it's a branch. Of course, you guys know that mimics and helps human intelligence. There are also a lot of economic benefits, and it also has the potential to transform the healthcare industry because there is so much data that is not used currently that it would be really, really beneficial for the healthcare industry to start and predict and also have some kind of preventive medicine in order to decreases the cost of more serious problems. So this thesis come together with these three main. So this presentation provides several processing techniques and deep learning architectures for a wide range of biosignals and objectives. And some of the architectures were benchmarked in three different contexts. So first of all is synthesis, generation of data. Okay, authentication, that is based on comparing the data that you provide and the database to check if you are that person or if you are that person that you claim to be, and also the detection of signals that are different from what's considered as normal or non-pathological. Okay, so the study of these algorithms helps unveiling new knowledge about the intrinsic nature of biosignals as we observe what happens inside the networks. So here I'm going to give you a small overview, the context, biosignal processing. I will pass on to the architectures, the applications that I mentioned, the conclusions about this work, some future remarks considering how can this evolve and how are the next steps towards more efficient healthcare AI. Some contributions, references. Actually, this is in the end, and I'm going to give you some minutes of explaining what I did at NASA FDL challenge. So, biosignal is originated by the physiological process of living beings and can be measured and monitored continuously by appropriate sensor. Okay, so you have several body functions. You have your own behavior. You have different measurable systems that can be put into practice and put in and store in data and use them for purposes. For example, the ECG. The electrocardiogram, you use three different vectors, and between these two vectors you have like an angle of the electrical activity between those two sensors. the EEG, where you have several sensors that has a reference in one of the sensors and also one in the ear to attenuate noise and the differences between the different sensors. Also the EMG, that is based on the activity of the muscles. So every time that your brain wants to use your muscles, they have to send a message to the muscles in order to move them, and we can capture that activity, that electrical activity. The thermal, is basically, and the respiratory signal that's based on the contractions and contractions and expansions of your thoracic cage. Also, for example, the keyboard and the mouse could be also indicators of your physiological system, for example, your nervous system based on your behavior. One example that I wanted to focus is the electrocardiogram. Is one of the most used signals because of its characteristic trait, and also it's one of the most vital organs in our system, and also with electrocardiogram we can detect several pathologies in the human system. The electrocardiogram, this particular wave, it is based on different electrical activities and different functions of the heart. Okay, and we have here two examples. In the left, atrial contraction. In the right, KRS complex. That's when the heart beats. It's when the ventricular cavities they pump. Okay, so I will not explain this a little bit, but I want to focus a little bit on the biomedical engineering side of how I envision the work of the neuron and artificial neuron. Here, every time that the entries of the neuron suffer some kind of stimulus, it grows in action potential. And after passing a threshold, it triggers an action potential. So this activation, so we have here the input, also the weights, right? But this bias, I consider it as this activation threshold, because only after passing this activation threshold, we will gain, for example, in the sigmoid, the value 1. So as we increase the number of hidden layer, our networks become deeper. Convolutional neural networks, I will not explain this much, but it's based on convolutions of images where you pass on some filters or a matrix of weights, and then you produce feature maps, and you continue subsampling until you have a vector of features where you can deploy, where you can use a classification algorithm in order to check what's the output. The recurrent neural networks are very important in biosignals and time series in general, because they capture the essence of the dependency of the signal. These are both cells, the long short-term memory and the gated recurrent units. We are going to use both of these that manage the memory of the recurrent neural networks in order to learn long and short-term dependencies. So for the optimization, we can use the mean squared error and categorical entropy. At least these were the ones that we used, but for biosignal processing, you can be more creative. In terms of optimizers, we can use Atom or MES prop. For this type of signals, they are pretty okay. So in the state of so just to check a little bit, the state of the art of using deep learning in biosignals is something more recent than using deep learning for images, videos, and text, and for example, sound waves. So here we have mostly data human-made extraction and classification. So most of the deep learning applied to biosignal were published after 2015, after some exceptions if you want to check it out. Also, from 2006 to 2018, most of the deep learning was used for only for classification. There are some actually that's only used for classification with using human-made extractions, but nowadays they are transforming data, for example, into images, and then you can use deep learning algorithms just as you use in image. Also, nowadays it's more common to have only some sort of signal processing before, and then to do deep neural networks to take care of the machine-made feature extraction, but also the classification. So here we have some examples. For example, the detection of arrhythmias, and using CNNs, but also you can find using recurrent neural networks throughout the literature. For the application scenarios, at the time that I wrote the articles, there wasn't much work done in deep neural networks. Most of it was on the detection and the detection of arrhythmias, especially because of what I mentioned of the electrocardiogram being a very simple signal to use. So why biosignal processing? Deep learning algorithms are able to learn nonlinear and complex relationship between inputs and outputs. So it's highly dependent on the quality of the inputs. And normally, data that is recorded by this type of sensors, the ones with the contact electrodes or the gel electrodes, both have noise, even if the contact electrodes are less invasive. Non-contact electrodes are, for example, this EEG, where you have a sensor and you put it like this, okay? And so this is contact. When you have gel electrodes are the ones where you go to the doctor, you have to pull on a gel and stick with some kind of that gel, stick it in the skin in order to have more conductivity and less noise, but they are not isn't of noise, okay? It exists. And signal processing serves the purpose of cleaning non-relevant information and simplification of the signals. So sometimes we should increase the deep learning performance. The amount of data, the more complex the data that you input into the deep learning system, since we are dealing with biological systems that are not deterministic at all. The best way of doing this is to simplify the signals, being easier for the network to understand and how to cope with them. We are going now I'm going to start to explain a little bit. These are modules that you can put in different orders regarding what you are doing or what you want to use. You have the raw signal where you have resampling, noise removal, quantization, etc. Segmentation. Here, segmentation is not exactly how you see in images. It's more cutting off the signals, okay? You have also normalization, and then you apply the deep learning algorithms. I'm going to pass through some of them in order for you to have a notion once you start using signals to have an approach to use them for deep learning. So first of all is noise removal. Normally we use the smoothing filters. That is actually filters that make baseline wander, but in a small window in order to smooth the signal, like this example, or for example, in the ECG. This is very important to notice. It distorts a little bit the signal, so it's you should be very careful how you use this smoothing technique. It's actually a convolution between a Henning window and the signal. And the signal becomes prettier, but for example, the amplitude will decrease a little bit. So you have to make sure that you know what you are doing. Baseline wander removal. This is more for artifacts. When you have this kind of signal, normally you would just chop off like remove it, because it will hinder all the process. So we use the baseline wonder is basically calculating the average of one window and then pass it through all and remove it from each point. So you remove the average of a large window, and then this baseline wonder disappears. But of course, at some cost. But it's better to chop off this little bit than chop off all of this. Okay. Noise removal. You can use several methods, such as if a mean or standard deviation is removed from is far off a threshold, you can chop it off, and you will only have the nicest signals. And but you can also use a clustering methods, such as this agglomerative clustering, where you check the noise areas and you can remove them. I'm saying remove them, but this is not always the purpose. As you will see later, noise can be used exactly to detect noise. So not always we have to chop them off, but also it can be used as labeling technique, for example. Quantization. Quantization is the reduction of the dimension of the signal. Okay, so this is the exaggeration of a quantization process, where you select several steps. For example, how many steps do you want your signal to have? And it will have these little squares that is like a simpler version of the signal. It is quite used for sounds, but it's also applied for biosignals in this case. Clipping its histogram edges is also a technique in order to remove of reducing the impact of artifacts. For example, if we have something like this, and we cannot remove it, okay, we may have problems later on when we are in feeding data into the algorithm. So this is a good process of removing those unwanted amplitudes. So this is the amplitude histogram, and you just chop off a small percentage of the start and in the end. And you have something like this. Okay. So there are several normalization types. You have, for example, the absolute maximum, based on the amplitude, on the standard deviation, also the absolute maximum and minimum removal. You can use all of them, making sure that that is for the purpose that you want, and be aware of the limitations of each one of them, and how do you want to use them in your deep learning architectures. All can use a time window. Okay, so instead of doing the in all signal, for example, imagine that 2-hour signal, it's like a lot of data points. If you do it in one chunk, you can do it, but it's better for you to use a time window and then slide that time window, making this normalization, making sure that you are not disrupting the signal and changing it too much. But this is the nicest approach because of the artifacts. The artifacts I cannot stress enough. That is the main issues dealing with every kind of algorithm that you use for biosignals and time series. So this is signal segmentation, something that is why did I put this like something that is really important? Because this changes the way that the networks learn the signal. Okay, so this is a very, very sensitive issue. Okay, first of all, you cannot put all the signal into a deep neural network without it blasting the GPU. Okay, or having a memory loss. It's impossible. Only if you have small sized signals or if you downsample them a lot. So the idea is to segment, to cut into pieces, okay? But you must take care that there are relevant facts that you want to keep, and you also should have an overlap. So you have a region of overlap between both windows for the network to learn different angles of the signal. Okay, it's not, you should not ever, for example, using the ECG, center, for example, your signal with the R peak, because your network won't learn that well, and maybe it will not even learn the R peak because it's always on the same spot. So it takes for granted that exists, so it doesn't care about it. Okay, so it's very important to check different angles of the time series. Okay, now I'm going to start with the fun part, that is the architecture. So I'm briefly talking about this design that I created in order to simplify how the networks should be built. So we have here the CNN encoder, you have the CNN decoder, you have the RNN encoder, but can be encoder and decoder. You have the RNN decoder, you have the latent layer, that is like the future layer after the classification part of the encoders. And also you can use dense forward networks in order to classify or make a transformation of the signal. So in this configuration, the model learns to predict the following sample based on the previous ones. Of course, this is not exactly this, but they are mostly used in this way. This configuration might be used in order to make a model learn about the signal's morphological mechanisms. I will explain this later. This configuration only classifies the next sample, as the model does not absorb the complexity of biosignal with continuous values. Okay, so this is why we need to use the quantization. So if we use the whole all the amplitudes that exists in the signal, it will not learn. It will reach a capacity, and it will not learn beyond that. The network is fed with the time windows of the output will be the same time window defined by one sample. Okay, and I will explain this better. CNN with encoder and a dense module. This is normally how we use for images, for example, but in this case, normally we use 1D signals. We can use also 2D, for example, if you use a spectrogram, but for 1D signals, you can use a 1D convolutional network, and it works quite well. An autoencoder using CNN encoder and decoder. You have here an example of the network while it's learning electrocardiogram, and it can be used for feature learning. Okay, and it can be used, for example, for transfer learning later on. So this configuration. So here we have a CNN autoencoder, which learns the features, as stated previously. You have the RNN encoder, where if you stack several feature vectors and display them through time, and you put them in your RNN, it will learn the sequences of those features, and then you can use it for classification, for example. Other architectures are explored. For example, the generational adversary network for domain transfer, where here I'm using a R peak, so it's like stating where the R peak is. And if you choose and if you parameterize it to according to one style, for example, this style of ECG, it can create a signal based on what has been learned. Okay, this is a very simple process that can be used in order to learn signals quite well. So now the application scenarios. First of all, the synthesis, the authentication, and then the detection. So in the case of the biosignal synthesis, I used the encoder decoder RNN. So it's a simple RNN. The objective is to create more data and to make the network learn and replicate the mechanisms behind the biosignal generation. So the idea is for to make a network that dreams about biosignals. So it creates biosignals only inserting noise to its to this insert. I actually have some exercises concerning this. If you guys are interested, I can always share the link for them. These algorithms were tested and in synthesizing three types of biosignals, the thoracic mechanogram. So it's like the contraction and retraction. Electromyogram of one guy pedaling a bicycle the in the in one of the muscles. Okay, and electrocardiogram in normal conditions. I use so this is an example of how we can do the processing, moving average and normalization. Okay, convolution with Hanning window. This is the smooth, as you can check the differences. I clip the histogram and then it becomes like all lined up, as you can see in this example. The architecture is so we have here the input sample. Since it's a quantization process, all the inputs are integers. Okay, it will pass through embedded matrix. That index will select a column of that embedded matrix and will pass on to the first screw layer. The screw layer will make transformation and will pass on to other two screw layers. And you have a regression node, the softmax mode, and you'll have a probability of the next output, the probability of the value that the next output will have. So ideally, this O1, O0 will have the highest probability will go for the value that will input here, okay, in X1. And that's why we have to dephase the windows by one sample. So we can have the inputs, the normal signal, and here they are phased like one sample because you want to predict the next value. Okay. So for training, you can use Physionet. There's a lot of biosignal data there, loss function, categorical cross entropy, optimizer, the RMS prop. The cross validation, I use the measurement of the mean squared error between the predicted and the input. And each model was fed with windows of the same source signal which trained the model. Other records of signals of the same type, not trained, which not trained the model, and between the one that trained the model and other types of signals. Okay. So this is an example, true example of two different biosignals that were synthesized. Okay, so they are given two different noise values. This one was given here 55, I guess, and this one was given the value of 32, no, 41, I guess. And it created this biosignal from that. So here, for example, you see that the signal lost itself, but then it started to recover. And this is a really cool trait of this biosignal synthesis, because once the model seems like it lost its track, it suddenly started and continued to synthesize the signal. Something very important for you to synthesize signal, the signal should be periodic. So it should have like signatures that are recurrent, or else you won't learn that much. For example, this EMG, it was like pedaling a bicycle. Okay, so it has always the same. So it's like tung 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 tung. When you do this, you have a contraction, right? So these are the when you have a contraction, and since you have several periods that are almost spaced at the same time, you can have some kind of representation of the predicted signal. And as you can see, there is much less noise from the source signal, but something that is very important, for example, the CMG, it can be comparable with noise. So it's normal to be it's normal to not have these disparate values, for example, the ECG. Okay. Something important that I seem that is quite interesting to look is how the signals learn. How the network learns the signal. So this is the recurrent neural network that while it was training, I saved the model after some epochs. So before in zero epoch, it will learn like nothing, right? It didn't even run, so it's completely noisy. And then you start to see some forms in it, and then it discovers that there is some kind of R peaks, and then it can describe more else which are these different forms, waveforms, and then in the end it gains a sort of sensibility to the frequency and also the continuity of the signal. So after the R, the KRS, you have a T wave, and then you have a P wave. So and this procedure repeats. So it learned this. We can also check that the hidden states of the layer, that every time that there is a KRS, there are disruptions in these outputs. There are some disruptions over here as well, but it's exactly on the T wave. Okay. From synthesis to authentication. So after developing this algorithm, we made an hypothesis. Model A is trained with ECG of person A. When the model A is fed with ECG of person B, the prediction error is higher. When fed with ECG of a person A, the error is lower. Okay. So this was something that we wanted to check it out, and it actually was true. So after checking the lowest error of simple, we understood that this has the potential for biometric systems. Okay, so what is it, ECG biometry? So ECG biometry is so there are several aspects that make the ECG a suitable input for biometric systems. Biometric systems are the ones, for example, the ones that are you can use, for example, your ID that has your fingerprint on it. It is for authentication. But if you use, for example, this ID, for example, on your iPhone, where you put your finger in order to unlock, or your face in order to unlock, those are biometric systems. But in this case, it's not identifying one person. Is you say that you are you, and what the algorithm is saying is if it's really you. Okay, so this is authentication. Two algorithms were tested while performing identification and authentication based on the ECG signal. The first one is based on the technology we saw before, and the next one is a time convolutional neural network. That is a convolutional neural network, but it's 1D and used for time series. Okay, it's not that special. And so the identification, the validation must be made by accuracy, and authentication is based on the equal error rate. So, and I will explain this later. And the recurrent neural network and the time convolutional neural network. So here, the time convolutional neural network, there are two different networks. Okay. There are two different networks. The first one is for non-fiducial ECG. Non-fiducial ECG is extracting a bit of the ECG and just use it. Okay, it's like it doesn't mean where you extract that window, and then you chop like a piece of the signal regardless of where you center it. And that another one is a fiducial system. So you always center on the R peak, and then you have the template of one cycle. Okay. I said not to use this approach, but if we use a mixture of both, of course you can use, but if we use a mixture of both, is more, we can have a network that also regards our waves and consider the ECG as a whole, and also as a window. So in the end, we fuse these encodings, and then you pass through a dense network, and then you have the classification. Here the classification is so I use the score. There's actually the low error, the Fantasia, MIT BIH, and SIB high. Okay, there are three databases that we used. These both are clinical grades, but increasing in noise. And this one is actually off-person ECG, where you measure on the fingers. The identification and the authentication. The equal error rate is based on the false negative rate and false rate and false positive rate when both are equal. Okay. And we have some really nice results concerning these algorithms. State of the art, as you can see here. Okay. At this time, I asked myself, is it possible for a deep neural network to learn the default morphology of a normal sinus rhythm signal, and with that identify the diversions caused by an occurrence, for example, noise or arrhythmia? So the objective is to predict when something different from normal signal of an ECG occurs, and it was tested in two scenarios. One is noise, and the other is arrhythmia. And here we have an example of arrhythmia that is premature contraction, okay? And also example of noise artifacts. So here we used the Fantasia from Physionet. Here we use Fantasia in MIT BIH, and the arrhythmia, the MIT BIH arrhythmia that is commonly used for several cases and several classes. The optimizer was the MS prop. The autoencoder used the mean squared error. And the noise and arrhythmia detection, we used the categorical class entropy. So in this case, we use the autoencoder to learn the features. And so we reproduce the signal, and we keep this latent factor, and the differences between the latent factors we can see using t-SNE. Okay, that is like so you can see the signals in two dimensions. Noise detection. After training the encoder with the autoencoder, the architecture was added with the dense layer, so we can use then the classification. So first we learn the autoencoder, okay, and then we use this without learning more the autoencoder, or just fine tune this segment in order to make this. So this is an example in how autoencoders should learn. Okay, as the autoencoder learn how to reproduce the signal, the noise, the loss will also decreases like this. So after that, in order for us to detect arrhythmias or predict arrhythmias, we are going to use several time windows spaced by time. I can explain to you later if you are interested in this. And it creates a lot of feature tensors that are going to be stacked by time. We do a dense transformation of the signal in order to input to the GRU layers. This dense is only a transformation, is not for classification purposes. And then after passing through GRU using a sequence of X windows, we have a fully connected network that can give us then the outputs, so the predicted if we are going to have an arrhythmia or not. This is not these results are good, are not state of the art, but because we sacrifice the performance versus the versus the generalization. Okay. So what was learned? What is the usefulness of these architectures in the future? So innovation in the capacity of learn and replicate several signals. In the case of authentication, we showed good results using deep learning and the detection. We believe that we created a system that could learn how is the normal configuration and how to classify it according to its divergence. Of course, um, this is actually very practical because, for example, if you have an extended amount of data and you check the divergence of the signals, the doctor can pinpoint the most important sections that should be used. So there are several approaches to using the future. For example, the fusion between networks using a hierarchical multimodal approach, where we have several architectures trained in different things and then have an output that is like the most more informed decision. Explainable artificial intelligence by the visualization of filters through generation mechanisms and also using an ensemble of other machine learning techniques in order to check its capacity. And AI in healthcare is the fusion between several artificial intelligence in different areas in order to have a more informed decision. So now we'll pass on to the generation of simulated biosensor data. That is, it was an initiative from Frontier Development Lab, okay, in partnership with several industry and also NASA. So here I was at NASA Ames. So there are several centers of NASA. You guys know already Houston, you have a problem. And also you have here the Kennedy Space Station, but you have also, for example, Goddard and Glenn, but I was on the Mountain View that is in the Silicon Valley. I also worked in the SETI Institute, so this was where we mostly did our job. The SETI Institute is Search for Extraterrestrial Intelligence, but nowadays they are more focused in searching for exoplanets, also searching for biology in extraterrestrial systems, looking at the exoplanet's atmosphere to check if it's possible to have life in there, and also very interesting topics regarding this. For example, also sun, how the sun affects us all here in the planet, between other. The FDL, so it's a project that occurs every year. This year it's already currently, but check out next year's. You should check if the next projects over here. They have partnership with NASA, but also with Google Clouds, the SETA Institute, IBM, Intel, NVIDIA, like big names. Mayo Clinic, and also there is a community of high performance people from everywhere in the world, in the brightest university, the brightest minds, but it doesn't mean that you are not a bright mind. So I got it there, so you guys can get it there as well. Okay, so I'm over there behind Critica doing this. So there were several challenges. One of them was living with our star. There is basically the impacts that the sun has in Earth, but also in terms of visualization of the sun, of the different magnetic poles, of how things work on our star. The moon for God is we are going to explore the moon again, so it's more about where to land, something like that. Astronaut health, it's concerning the health of astronauts. That is quite important, as you're going to see, and also mission control for Earth is in order to prevent major Earth, not prevent, but predict major Earth changes, for example, floods, fires, and other things like this. So these are the researchers. We have Eleni, me, Kritika, and Brian, and also AI mentors from the NASA, but also from NVIDIA, IBM, and the CSA, the Canadian Space Agency. So we are going to the moon again by 2024. At least this is what NASA says, and believes this. And we are also already projecting going into Mars in the late 2030s. So these are very exciting um, moments, right? Because now we are going back to the moon and we are going to explore Mars. It's like a new breakthrough in our technology. But as we go further out in space, we lose contact with our Mother Earth. Okay, so we lose its protective mantle. We get out of the communication. So, for example, if you want to send a message to Mars, it takes 8 minutes. Okay, but the thing is not the 8 minutes. It's like a few bytes take 8 minutes. So real-time monitorization in health in space out of it's not possible in the meantime. So what we think is that an automated and the astronauts team normally are composed of 4 people. One of them, the medical practitioner, normally is also a psychologist, and also if it was a complete and also a medical doctor doesn't know everything that may happen in a spaceship. So it's very important to have some kind of automation system that could monitor the health of the astronauts. And the astronauts undergo to several changes in their physiological body. One of them is radiation that can stimulate neurodegenerative diseases, such as always stimulating through the radiation. The astronauts, when come to Earth, sometimes they close their eyes and see that lights in their eyes. That is the result of overstimulation of the nervous system. Also, cancer risk, of course, and different types of radiation could interact with your DNA. Motion sickness, this is very important in order to balance your physiological measurements. So the motion is not only for you to stay in erect position, is also directed into the control of other physiological systems. Bone mineralization, kidney stone formation due to bone. So there are a lot of things, and one of them is the changes that makes in the heart. Um, so the thing is that when you pass, for example, 1 year in space, what happens? One of the things that happens is that your heart it's elongated, and if you take long periods of time into space, you have your heart starts to be more round and to lose muscle. This um, From this may arise several problems, such as several arrhythmias. There is a change of electrical activity of the heart. So, changing the shape of the electrical activity of the heart, okay, it changes. Changing the muscles of the heart changes the way that the electricity runs throughout your heart. Okay, so there are differences, and they result in complications resulting to that. Which are the complications? No one knows, but there are several indications of problems that may arise. Okay, and NASA has a list of them, and one that we focused on is atrial fibrillation. So nowadays, wearable devices for health monitoring enable a quantitative understanding of changes for the diagnostics and intervention. So this is a garment that Jean-Pierre, this astronaut, used that collects several biosignals in real time while he's doing performance several activities. But the astronauts are extremely healthy. They do not have health issues. If they did have health issues, they would not go into the space craft. Okay, so into the ISS. So we have data from the wearable, but we do not have any kind of problems regarding that data. And we aim to, so we need that data in order to train other machine learning algorithms, because the types of the the wearables data are different from the clinical grade data, the ones of the gel electrode. So we aim to synthesize symptomatic wearable cardiac data to enable and empower tools for diagnostics and prevention. So the asymptomatic and symptomatic ECG. So an healthy one, I already shown you, the atrial fibrillation has several perturbances on the P wave, okay? And sometimes it doesn't have a good representation in the T wave. This because both of these are related to the atria, okay? So the methodology behind this is from clinical, since this data does not exist in real life. How do we know that we are creating the right, if we are going in the right direction? So from clinical asymptomatic, we create astroscene asymptomatic, we code for the style, and the clinical asymptomatic or clinical symptomatic, we code for the content. Okay, and we create astroscene asymptomatic. Okay, yes, this garment is astroscene. Okay, it's the wearable. We use several public databases, but we also use data from air missions that are the missions that they go to really difficult places and be isolated for a long periods of time. NASA data that was recorded at NASA AIMS, and also CSA data that was recorded in the CSA data. We did not use astronauts in space because they are very sensitive to that data, and we don't have much records, so it's impossible to retain the anonymous data of the astronauts. We based our approach in StyleGAN, where we have the core styles copied, and the source and the destination, in our case the style and the content. So this is the wearable style, where you have several a noise, like underlying noise. There is also some kind of baseline wonders and etc. And also the symptomatic content, where how as I shown you. So the architecture. So we have two autoencoders, one for style and one for content. So this is content, this is style. We so encode the feature vectors for each autoencoder. Then we fuse both latent layers using concatenation in the fusion module, and then we pass on to the generator, which will mix both these inputs and create something. Okay, this something would be the mixture of both. Then we will pass on to two discriminators that are CNN classifiers. This one checks it if it has the style, and this checks if it has the content. Okay, so this is the return of the loss function. So we pass on the information from this discriminators into the generator, but also to the encoder, in order to fine tune these features in order to reproduce better mixture. So in the end, we only use the generator in order to synthesize the signals. So these are several model inputs. It's not perfect, but it's the first step towards something that is quite fascinating. But it's really hard to validate if this is good data or not, since the only ways of validating this, it would be to compare with real signals, but real signals do not exist. So the approach that we had is first check the embedded, so the latent factors of the different signals, and this is what we get. The dark is the clinical symptomatic. This is the wearable symptomatic. This is the mixture of both. So it's exactly how we want it. And we use the simple approach of our model using only mean squared error. Okay, so we don't use the discriminators here. And we see at least is better than the one that we first thought. So these are the conclusions. We have there were a small clinical validation made, but this is for future work. We want to expand this to other signals, not only atrial fibrillation, and also a continuous using recurrent neural networks instead of convolutional neural networks. So I have here a small video that I wanted to show you. This is actually an astronaut that is working at the ISS. It's not live, but it was when it was recorded. And it makes like the perfect view for this kind of approaches. You know that space is vast, and the best and the brightest go out to space. But the thing is that we are doing things for space, but after doing things for space, we can look back into Earth and check how can we use them in Earth. Okay, so how can we use this in Earth? For example, in remote places, in impoverished populations, in places where the medical doctors are not available at all. This could be like a really nice solution for this type of systems where we could create data in order to use it for later on and create automatic systems. So thank you for your attention. Let's see if you have any questions.
Thank you very much, David, by the great talk. It was certainly enlightening, for me at least, that I'm from the same area as you. It was a great talk. So I think we still have a small time for a couple of questions because you basically ended perfectly on time. So let me start with this question from Rui. He asks, are the synthesis models trained only with ECGs of a single person? So I believe this maybe refers the NASA question. So do you train like patient-specific models to generate signals from that specific person that you want to predict?
So first of all, it's like I'm going to talk about both situations. So the first synthesis that I mentioned, yes, of one person. Because they have each person has his own traits. So the ECG signals, if we mix up everything in the same model, the general approach won't look good once you synthesize it. There is one way of using the same, but you have to parameterize it in order to make sure that you know the style that you will want. In terms of the NASA, no, it was not of a single person. It was a mixture of several people, and so as training, we did a mixture of several people, several situations. But once we are generating, no, it's not one person. You can put one person. That would be the ideal scenario. But at the time, we did not have the same person with atrial fibrillation, for example.
Okay, yeah, because I believe if this were to be implemented in space, my first approach would be to try to get like normal data from this person that we know that it's going to be sent to space, and then try to generate some artificial data that would look like how this person would have some kind of problem. And so
exactly.
But we would need to have the data from that person. So that's one.
So the idea would be exactly to train the algorithm several people with several conditions, etc., and then fine tune it to that person. And then we can, and once you put as input that person, it is expected that that person ECG will change.
And while we are in this topic, do you think that maybe this could be used to other kind of signals, not just the ECG, right? You can maybe try to predict other problems from different biosignals in space. I don't know which ones, but maybe, I don't know, like seizures. I don't know if there is a different kind of behavior in like seizures in space. I don't know.
Yeah, I also, no one knows because I don't think that anyone had a seizure
Yeah,
there.
yeah.
So it's exactly that. There are several biosignals, for example, the respiratory signals. You also may extract signals from the nervous systems, from the beats per minute, for
Hmm.
example. You can also have the sensors for temperature, but temperature is more difficult because you have fluctuations of temperature throughout time. If you have some kind of periodic effect, yes, you may use it. And there are also others, for example, EMGs, if we could use EMGs, yeah, of course, but they have to be periodic. That is
Of
something
course.
very important.
Okay, so let's now move to a question from Luis. Uh, he asks, fairness is the main issue in biometry applications. How do racial and age gender biases take form in the area of biosignals? What are the main ways to detect, avoid, and correct these biases in the field?
Okay, so this is a wonderful question. I must commend Luis. I think it's a really interesting question that everyone should be aware of. In the biosignals domain, it's very difficult to access this kind of data. So why is that? Because normally when you have the data in your possession, it's already filtered because we cannot know, for example, the age maybe, the race, not really, the gender. It's very important when we are using records of biosignals and also things that are related to the physiology. There must be a percentage of women and of men, and also, or if there is some kind of now all the databases have this in concern in order to check which kind of populations we are using. In terms of racial, I don't know if this is an issue because at least from our concerns, biosignals, at least at large, they are much alike from different ages. They can be supported by environment effects, but I don't think that races are a major concern. But in order to avoid that, the information should be done in recording the data when the data is recorded, because I don't think that is correct to synthesize this kind of data because it could even enhance the biases. Okay, so the main ways to detect, avoid, and correct these biases in the field is, first of all, check the database, check exactly what kind of data you are using, check all the statistical information that they have on the data. If you are the one acquiring the data, make sure that you annotate all these records and then make a statistical inference in order to make sure that all your classes are well distributed and well made. If not, then, for example, you can augment data, but not regarding the ethical issues, is more regarding the pathological lack of data, because this is also a problem in biases. If you have low pathological data of one kind, it's much less probable that the algorithm will detect it. So it's very important also to create these biases of different classes. And if you don't have enough classes or enough time windows to support that class, then you should augment it because there's no other way. Because you don't want to have more diseased people or inflict so these other ethical issues that I don't want to get into.
Yeah, great question by Luis. So we also had a couple of comments asking for some references like books and papers, um, yeah, into the application of deep learning on different biosignals. And also people have requested if you share the exercises that you mentioned before. So do you have any kind of like one major book that you recommend for people learning
My
this?
thesis. uh, as I can say, In order to go deeper into biosignals, I don't know the name of the book, sorry, but there is like I know the name, but I don't remember. It's something. It's about. It's like the book of biosignals, but in terms of applying deep learning to on different biosignals, I don't think there is a book yet, at least at my knowledge.
Yeah.
When I started my PhD, there was no there was some knowledge of it in the biomedic community, in the biosignals community more specifically, but it was not that well developed. So if there is a book, I guess there will be in ECG, electrocardiograms, because those are the ones that are more used, and I think they may want to publish a book. Okay.
Yeah. Yeah.
Anyways,
Anyway,
yes, yes.
yeah, I was just saying that we will like this video, the video of the presentation will be on YouTube, and also we'll make sure that the slides are provided on our GitHub page. So if you want to use like this as a reference, yeah, it's okay. People can go come back and watch the presentation, and we can also add some links to some books at the end of your presentation for reference.
Okay, great. I also will share the exercises. Yeah.
Yeah. Okay. Now moving to João question. In space, there is not alternative, but down on Earth, most people would question an ML model. In your perspective, how can we increase the odds of seeing our models being used in practical medicine?
The odds are pretty high, actually. Here in Portugal, we are there are the hospitals that are starting to implement this, mostly in private hospitals, no Hospital de Luz and Lusíadas. In the United States, it's starting to get mainstream. So the odds are really high, because I think that the doctors are already overburdened with all the information that they have and they have to deal with. That this kind of problems will help them a lot in not replacing their job, because it's not at all, at least in my perspective, it's not, it's completely impractical. But in order for them to look at some problems that may arise, okay, for example, there are some kind of images of imageology, sorry, that you can use these algorithms to pick differences in colors that the human eye cannot perceive. So it can help the doctors if they are tired, or in order for them to have a better, helping them doing a better job. So I think, yeah, the odds are pretty high. Yeah.
So you don't agree with Geoff Hinton? That's said that radiologists will disappear until 2020. Now we are in
No.
2021,
Yeah.
so we already passed the date. But
No, man.
he
No,
said
no,
that.
no. The human health is too important to be dictated by a machine, and also the machine does not know everything at
Yeah.
all. The,
So I
the,
guess
so the thing is, from my perspective, the AI is it's very specific to the problems that you want to find. So if and the human mind can perceive some things that is the not the problems that you are focused on. Okay.
okay. So moving from to the question of Boyan, can we combine data from different devices in order to train the same model? For example, signal from Apple and Samsung smartwatches. Do we need some preprocessing?
You always need pre-processing, especially because they have a lot of noise. In the BPMs, it's normal to have some weird things going on, like you having 200 BPMs is not healthy at all. And sometimes you're having zero, for example, when you don't have the watch and it's still collecting some kind of data. So you always need pre-processing. You cannot get rid of that part. Special, and also you have to segment the signals. Yes, you can combine both types of data, but take into regard that most they may be different, but mixing both mix them mixing them together, I think is the best approach, so you can have a more robust system. So if you have like Samsung, Apple, Wiki, Waka, Wooka, whatever brands that would have like different these type of signals. If you put them in the same model, it will be more robust. So go ahead and do it. Yeah.
Okay, so I think we are getting short on time, so I'll just select one more question. That's okay. So, how hard is it to train a style GAN for signal processing? Do you have any heuristics to succeed on this task?
Okay, so the toughest part of this algorithm is exactly
Do you want me to?
this
You're showing the
training.
screen. Do you want me to?
Yes, please.
Okay,
It's easier.
that's
So
that's
the thing is that the most difficult part for this is exactly the training. Why? Because first you need to train the discriminators. So in order to check what is noise, what is style, and so which style it has, okay? The contents, the same thing. And then you train the autoencoders one first time. In the second time you train the autoencoders, you have to input this loss and from this style. So we did several steps on training this because there is something called the feature disentangling. That is like, so you don't want these features to be available here, and you don't want these features to be available here, or separate most of you want. So you want to this content discriminator be really good at describing the content, but really bad in describing the style. So we have to train this encoder in a way that disentangle the features, okay? And also for this side. I can explain this better if you just send me an email and I will answer it. And then we have to train the generator using the style and the content. And so you have 4 stages for training. Okay. Also, one step that I did not mention is that these are combinations. So if you want, you can have infinite combinations, right? Because you have this window with this window, but you also have this window with this window. You also have this window with this window. If you want to have this window with this window with that window, so you can have like infinite combinations for this. Okay, so as my essay, in terms of loss function, I can say that the autoencoder used the mean squared error. Okay, this was the categorical cross entropy, the binary cross entropy, because it has the style or it had not had the style of the wearable symptomatic. Okay, here also binary, clinical symptomatic or not. And then we used, in order to fine tune the encoders, we used that discriminator like 1 divided by this loss times this loss. Okay, so you have a reverse, but you have to make sure that will not get infinite because of the
I think
zero.
that Luis already answered. He said that yeah, he thanked you. And
Okay,
think,
okay, great.
yeah,
But I can write me an email and I
yeah.
can
Luis
answer.
knows. Yeah, if he wants to a further explanation, he will write you an email.
Okay, great.
So just to wrap up, thank you very much, David, for this great presentation once more and for answering these questions. I just want to say 2 quick notes. First is that we have two forms on the YouTube description that we want people to fill. If you want to have different topics in our meetups, please feel free to suggest them, and also to tell us how did you like this presentation. And also please don't forget that next Monday we'll have a reading group on self-supervising learning. If you want to join, the link will also be on our description. And so see you all next time, and thank you once more, David. Bye.
Thank you for having me. Bye bye, guys. See you.